Hello students, so let us continue. So let us start with some important representative, some important compounds or representative elements. Let me start with the boron halides. Boron halides, now you can simply represent like this Bx3. It can be Bf3, BCl3, BBr3, Bi3. So these are the boron halides which I am going to talk about. So talk about boron halides, they have a general trigonal planar structure. Let me represent Bf3, have a trigonal planar structure. Trigonal planar structure. Why it's so? Just think about no electronic configuration of boron having an atomic number that is no 5. It have a configuration 1s2, 2s2, 2p1. So the number of electron available in the valence shell is not 2 plus 1, which is equal to 3. 3 electrons are available in the valence orbital, which means now 3 electron is available. So it can form 3 bond pairs. So 1, 2, 3, 3 bond pairs it forming, and there is no lone pair is there. You can see no electron present as unpaired in the valence orbital. So 3 bond pair and 3 bond pair and 1 lone pair. Sorry, 3 bond pair, 0 lone pair. 3 bond pair and 0 lone pair, which means no they can adapt a perfect structure that is trigonal planar. So that's all about no the first point. The boron halides have a perfect trigonal planar structure. Now let us think the acidity. We know when you talk about boron halides, the first thing comes to your mind is the acidity. Boron halides are Lewis acids. They are Lewis acids. So why they consider as Lewis acid? Because no, according to Lewis concept, acid is a lone pair electron acceptor, while no base is a lone pair electron donor. If you again now check the electronic configuration, you can see it have a boron have a electronic configuration 1s2, 2s2, 2p1. So now when it is excited configuration will be 1s2, 2s1, 2p2. So let me draw that. This is 2s1 and 2p 1 2. Okay, you can see this is the 2p subshell. So you can see there are now 2 electrons in the 2p subshell, and they undergo sp3 hybridization, sp2 hybridization to get that trigonal planar structure when they form boron halides. So sp2 hybridization they undergoes, they forming a trigonal planar structure. You can see an empty orbital in the p subshell, which means now empty orbital is available. That means it can accept a pair of electron. One pair of electron can be accepted by this empty orbital. That why now boron halides can act as a good Lewis acid. So now let us think among the boron halides what may be the order of acidity. It's interestingly it is observed that Bi3 is more acidic than BBr3, which is more acidic than BCl3, which is more acidic than BF3. Normally, one can think fluorine is highest electronegative element, so they thinks in a manner in which BF3 they thinks more acidic, but it's not so. Why Bi3 is more acidic compared to BF3? Yes, here now we have to think about now if I talk about BF3, which is no among the boron halides which is having lower acidic Lewis acidic nature. Why it's so? Let us think. Because now we have when we talk about no acidity of boron halides, you have to think about Lewis concept. You have to think about no if the boron halide experience high electron deficiency. High electron deficiency is there, then it become a better Lewis acid. So talking about boron and fluorine and boron chlorine, boron bromine and boron and iodine, you have to say boron iodine, boron and fluorine have comparable size. That's something that no you cannot. If you compare no these boron halides, boron fluoride coming in the same period, that's coming in the second period, so they having a similar size. Similarly, now talk about orbitals. Here now you can see the electrons present in the fluorine atom, it should be in the 2p orbital, and also now electron talk about the electron present in boron atom, that also 2p. So the electron are present in the same orbital in the case of boron fluorides, while now it will be the final electron will be present in 3p. In the case of BCl3, it will be 4p, it will be 5p, etc. So that means now in boron the now empty orbital are present in 2p, while now as we move down you can see the energy difference between the orbitals increases. So which means now the energy difference increases means now there is no real kind of an overlapping that is possible in the case of boron iodide if you compare with the boron fluoride. Now let us start thinking why no electron deficiency is there. Because we know fluorine having an atomic number 9, having a configuration 1s2, 2s2, 2p5. So 5 plus 2, 7 electrons are available for bonding for fluorine. But now when you talk about bonding here now, one fluorine atom actually only involved, one electron is involved. So rest you can see the 6 electron that is present in fluorine. While in boron now you can see one empty orbital that was present when now it forming a boron halides, you will see one empty orbital is present. So there is a possible electron transfer that can take place from the electronegative atom, that's electronegative halogen, to the empty orbital of this boron atom. So there is a pi electron transfer that is take place from halogen to boron simply because of the two reasons. One is now boron fluorine have comparable size. Number two, they have a comparable energy. So there is a electron transfer takes place that we will call pi back bonding. So because of this p pi back bonding, you have to say the boron atom now getting some electrons from fluorine atom, which makes them now less Lewis acidic, because now if the boron atom is more electron deficient, it will be more Lewis, it will show more Lewis acidity. But the problem is because of the comparable size, because of the p pi back bonding, the boron is not getting some electrons, so it's not that much electron deficient. So if you compare the boron iodide, here you can see now iodine having a bigger size compared to boron, and the energy difference between the electron present in the halogen atom and the boron atom is very much different. So it's not easy to have the p pi back bonding easily in boron iodide. That why boron iodide experience highest electron deficiency, which means it's a better or highest Lewis acid among the boron halides. So that's a point you can remember related to Lewis acidity. Now let us discuss another boron compound, which is one of the important compound in for as far as boron is concerned. This is the simplest boron compound that I am talking about, that is diborane B2H6. Diborane. Now, boron do not form BH3, which is unstable. So, simplest boron we consider is B2H6 diborane, because now it has BH3 is unstable, so it quickly combine with another BH3 unit to form B2H6. So that is the simplest boron for you. And when you talk about the preparation, first let us we are talking a lot about diborane, and let us start with the preparation. There are different methods are discussed. So one of the method of preparation is actually from boron fluoride, boron trifluoride, when it's treated with the sodium borohydride. Sodium borohydride. Sodium borohydride is one of the reducing agents that used in our organic synthesis. So what good about it can provide hydrogen. So it will directly convert it into diborane and subproducts is also forming, that's NaBFO, sodium borofluorides. So if you balance it, this will be 4 moles of BF3 is react with the 3 moles of sodium borohydride to form 2 moles of diborane and 3 moles of sodium borofluoride. So that's the first method of preparation from boron fluoride. Let us talk about the next method, this time from boron trichloride. This time lithium aluminum hydride is another reducing agent that is used, which is now more powerful than sodium borohydride. So again you are getting diborane and the subproduct will be the lithium aluminum chloride. Lithium aluminum chloride is the subproduct that you got. So if you balance it, it will be 4 moles of boron trichloride react with the 3 moles of lithium aluminum hydride to get 2 moles of diborane and 3 moles of lithium aluminum chloride. So that's another method of we're talking about preparation of diborane. So that's the two method that I discussed. Then now talk about now another method. This time boron trichloride. Boron trichloride. Now hydrogenation is carried out in presence of electricity. So electrical discharge. Electrical discharge is carried out. So that now you are getting diborane and hydrochloric acid. So this is hydrogen chloride. So these are the another method of preparation of diborane. Any three that you can remember. Now still more method is diborane also can be prepared from sodium borohydride. Sodium borohydride, which is treated with phosphoric acid, that's 3PO4, phosphoric acid to give diborane, that's another method. This time side products are Na2HPO4, disodium hydrogen phosphate, and hydrogen gas will be released. So it will be sodium borohydride react with the phosphoric acid to give diborane and disodium hydrogen phosphate and hydrogen. Next, method number 5, this time sodium borohydride treated with iodine. Sodium borohydride treated with iodine. So this time now here using a solvent that now we call diglyne, which is now a ether solvent. So in presence of solvent to give diborane and hydrogen and sodium iodide. Sodium iodide. So that's the next method. Now the final method, this time from boron trifluoride again, BF3, and react with sodium hydride to at a very high temperature 180 degrees Celsius to get diborane and sodium fluoride. So these are the important methods of preparation of diborane. Okay, diborane is one of the important borane that now we can remember use about the preparation of many organic and inorganic compounds. So such a important compound is diborane. So you can remember any three best method. Now talk about properties. Yes, diborane existing as what? Diborane is existing as gas at room temperature. Something that you can remember. Okay, talk about properties, physical properties. The existing as gas, which is an inflammable gas. Something no. You should remember inflammable gas and it's colorless, toxic as well. No, very repulsive odor. So these are the properties that you can remember: it's a gas at room temperature and it's colorless, toxic, and inflammable. Talk about stability. Yes, diborane is reasonably stable, but no, at a high temperature it decomposes. So diborane decomposes at high temperature to get higher borane. So that is no, not different type of diborane. B4H10, it's a higher borane that now generally you get when you heat diborane. B5H9, then B5H11, V6H10, etc. That's the way it goes. So what's the process is actually diborane is now when it's heated at higher temperature, it converting into higher boranes. That's one of the property of diborane. Talking about stable, is reasonably stable at room temperature, but decomposes at higher temperature. Action with the oxygen. Yes, diborane do undergo combustion reaction. So diborane is highly exothermic in nature. That means huge amount of heat will be released. Combustion means heating in presence of oxygen. This time now diborane is not hydrocarbon, it's diborane, right? So boron oxide or boric oxide we will get. Then now water. These are the products that you are getting. So here now remember. If you don't remember the value, that's okay, but how much exothermic it is? 2160 kilojoule per mole. This is highly exothermic. That point we should be careful with the diborane because it's easily undergo combustion reaction to get diborane. So diborane undergo combustion reaction to form boric oxide or no boron anhydride. Such names are there for B2O3. So that is the action with oxygen. Now talk about action with water. Yes, diborane do react with water to form orthoboric acid H3BO3, which is one of the weak acids of boron, and we will discuss more about orthoboric acid in the later session. So diborane hydrolyze to get orthoboric acid. That's another product for you. So that's a reaction with the water. Talk about reaction with the alkali. Yes, it do react with alkali. Diborane react with the alkali to form. Take sodium hydroxide as one of the examples. Sodium hydroxide in presence of water to get sodium metaborate. NaBO2, that we will call sodium metaborate, and hydrogen will be released. So here we are talking about now reaction with the sodium hydroxide. So in presence of sodium hydroxide and water, diborane is converted into sodium metaborate. So that's another product that we obtain when treated with alkali. Hydrogen gas will be released. So that is a reaction with alkali. Now talk about reaction with the halogen. This time now hollow diborane will be formed when it's treated with halogen acids like HCl, HBr, HI, etc. Again, now HI is more acidic than HCl, HBr, etc. Something now you have to remember. B2H6 plus HCl, which is to form B2H5Cl plus HCl plus hydrogen gas will be released. So diborane halide will be formed like no others. So one hydrogen of diborane will be replaced by halogen and hydrogen gas will be released. That's a reaction with the halogen acids. Now reaction with ammonia. Yes, it do react with ammonia depending on the proportion. It's if you take no diborane and ammonia in the 1:2 ratio. 1:2 ratio, first diammoniate of diborane will be formed. B2H6 to NH3. Diammoniate of diborane will be formed. This is just like now ammonia is a Lewis base having a lone pair of electron, that's simply forming a bond with this electron deficient boron atom. So it will be diammoniate of diborane. But when this is heated, when it is B2H6, when this is heated at high temperature, we talk about above 300 degrees Celsius, you're getting an interesting compound that we will call B3N3H6. That is diborane for you. Sorry, that is borosine for you. B3N3H6, that is borosine. Now talk about borosine. We will talk a lot about borosine in the later section. Borosine. One point you can remember about borosine that we call inorganic benzene. Very similar to the structure of benzene, but instead of carbon, here you can say alternative boron and nitrogen. So that we will discuss what is borosine is all about. So anyway, if you want to prepare directly borosine, you just treat diborane with ammonia at a high temperature. If you directly heat at high temperature, you will getting a diborane this time molar ratio should be higher. So 3 is to 6, that is 1 is to 2 again, but higher temperature. If you treat at high temperature, you getting borosine plus hydrogen gas will be released. So that's another method. Diborane treated with ammonia at a high temperature gives you borosine. Now another boron compound will form if you take excess ammonia. If you take excess of ammonia, you get a compound that we call boron nitride, which is a very hard substance. Second hardest to our diamonds. So such a hard material that we're going to get when diborane is heated at high temperature and in presence of excess of ammonia, that we will call boron nitride. We will discuss about boron nitride as well, the structure and the important properties. So that we will discuss. So these are the important properties. Yes, still more is there. These are the reaction with ammonia. So three important compound: diammoniate of diborane. That is when you take at low temperature when ammonia react in 1:2 molar ratio. Then at high temperature when that is even heated, you will getting diborane. You're going to get a borosine, which is called inorganic benzene. Then when excess ammonia is taken, another important compound that is forming is boron nitride. Next with the carbon monoxide. Yes, diborane react with carbon monoxide to form boron carbonyl adduct. So borane carbonyl adduct. So B2H6 react with the carbon monoxide to get a boron carbonyl adduct will be formed, which means a carbon which is having a lone pair of electron and oxygen also having a lone pair of electron. So here carbon actually forming a coordinate bond with the boron atom. So carbon monoxide act as a Lewis base. It will donate a pair of electron to boron to have that bonding. So that type of bonding we will call adduct. So borane carbonyl adduct will be formed at high temperature. And pressure of 20 atm. So that's borane adduct for you. It is diborane. Always boron compounds are electron deficient, so they act as Lewis acid, and here carbon monoxide act as a Lewis base. Now again consider another Lewis base. The similar kind of reaction will take place. Talk about amines. Amines are generally basic. So let me take one example this time. Triethylamine. Triethylamine is one of the Lewis base. When you treat with the Lewis base, you are getting diborane will be splitted, and you can see a you can see amine adduct will be formed. So nitrogen having a lone pair of electron, that's not forming a coordinate bond. Nitrogen having a lone pair of electron, that's forming a coordinate bond with the boron. So no amine diborane adducts will be formed. Similarly, pyridine. When it's react with the pyridine now actually having a structure C5H5N. C5H5N to form a similar kind of structure. So adduct will be formed. So this is now pyridine. You can remember the structure will be like this. Okay, so this is pyridine for you. So pyridine adducts. Again, no nitrogen having a lone pair of electron that can act as a lone pair electron donor. So generally, amines and nitrogen based compounds are Lewis bases. Similarly, talking about reaction with metal hydrides. When diborane react with the metal hydride like lithium hydrides, you getting metal borohydrides like lithium BH4 minus. Lithium borohydride will be formed. Similarly with sodium hydride. Sodium borohydride will be formed. Try to balance these two LIS react with the diborane to get lithium borohydrides and the sodium hydride react with the diborane to get sodium borohydrides. So these are now two important borohydrides that we generally use for the synthesis of many inorganic and organic compounds. So lithium borohydride, sodium borohydride can be prepared by treating lithium hydride or and sodium hydride with diborane. So that is an important reaction for you. Now finally hydroboration. Hydroboration. Hydroboration reaction is interesting where we generally use for the preparation of alcohols from alkenes and alkynes. So let us take an example CH2 double bond CH3. This is this we call alkene, unsymmetrical alkene when it's treated with the diborane. Diborane you can you can write like this HBS2 two times. So this is diborane because diborane in presence of diborane alkene do undergo reaction where hydrogen goes to the carbon atom which having less number of hydrogen atoms. So hydrogen goes here, BH2 goes here. So just opposite to the anti-Marconico's rule. So you're getting a product like this CH2 CH3 where this part BH2 will join. This part hydrogen will join. So you are getting CH2, CH3, BH2. So now if you simply hydrolysis in presence of hydrogen peroxide in an alkaline medium, actually getting a product. Now this BH2 will be replaced by alcohol. So this is one of the method of preparation of alcohol for you. 1 mole of alcohol will you get. Still now if you still treat this particular compound with another same mode of alkene, unsymmetrical alkene, what will happen? Again this will split into BH and hydrogen. So where hydrogen goes to this carbon atom and boron part will be here. So we are getting CH2, CH2, CH3, BH, CH2, CH2, CH3. So that's another compound you are getting. Now, if you still treat with another another alkene, that is now CH2 double bond CH3. Here now again this will split into boron and hydrogen. So hydrogen will go here. So we're getting a product. It's B CH2 CH2 CH3 CH2 CH2 CH3 and CH2 CH2 CH3. So alkane boranes you're going to get. Which on hydrolysis? Which on hydrolysis in presence of hydrogen peroxide in alkaline medium? You getting alcohol again, but this time not 3 moles of alcohol. So can you write 3 moles of same products? It will be CH3, CH2, CH2 OH. So this will be our final product. So hydroboration reaction we generally carried out for the synthesis of compounds like alcohol, where no hydrogen and boron part will be added across the unsymmetrical alkene against the Marconi-Cross rule. That means it obeys anti-Marconi-Cross rule. So these are the products that you're going to get when diborane treated with an alkene. So that reaction we will call hydroboration reaction. So these are the reactions of diborane. We can discuss the structure and more in the upcoming classes. Thank you.